Okay, so this is the second video in the line of best fit series. And what we're going to be focusing on right now is errors and the least squares criterion. So I'm going to walk you through little bits and pieces of a least squares analysis using the same example. And the first bit is I'm going to run some code just to show you how R can be used to make pretty graphs. So first let me see if I can get this figure here. Remember, we started with this figure where these are the observed values. Here are the observed values. X is 1, Y is 4, and so on and so forth. Don't need to redo that again. But if you notice that this line of best fit doesn't go through any of these individual observed data points. It's a line that cuts in between each one. And what I want to show you is that this line that cuts in between each one is the line of best fit because of the fact that it minimizes the residuals, and more importantly, it residualizes the squared residuals. So first let's talk about what the residuals are. And I've got this fancy little bit of code here. So I just did a quick for loop, and you're going to see what it does is it draws these little lines. Okay, so each one of these lines represents the length of the residual. So it's the distance in the y value that the observed value deviates from the expected value. So here, x is 1, y is 4, is y observed. And y expected is going to be someplace around here, looks like about 6. So you can imagine that this is going to be off about 2, right? So now how do we figure that out? Well, R gives us this handy little function called resid, and resid will take out the residuals. So down here, I'm just going to highlight this so everybody can see. Now you see it in blue. The first data point has a residual of -2. All right, so that would be y observed minus y expected. Okay, now y expected is y hat. Okay, for those of you who've gone through this before, and if you read my review, you'll notice that this red line, this is all y hat, and this is y observed, or oftentimes just typed in as y. And the way we get the residual is we take the observed and we subtract out the expected. So 4 is the observed, -6 gives us a -2 for our residual. So any value that is observed below the expected line, all of these will be negative. So you'll see here 1, 4, and 5 will have negative values. And sure enough, 1, 4, and 5 have negative values, -2, -1.1, and -0.8. Conversely, any value, any observed value that's above the line will have a positive residual. So if you'll notice that the signs here are going to be related to where the observed value falls. So the way I always remember this is positive residuals are above the line, negative residuals are below the line. So residuals play an important role because these are essentially the errors of estimation, or the errors in our expected value. That the expected value deviates from the observed value. Now, these residuals play a part in what we're going to do because they are part of what is the least squares. So the least squares means that these residuals, if we square them and we take a sum total, so it's this 2 minus 2 squared, it's going to be 4. Now why do we square them? Because there are going to be some positive values and some negative values. And so if we don't square them, by definition, if I just do a sum of residuals of LM, we know that the sum is equal to 0 right here. So the sum of the residuals is equal to 0. So you can't minimize that. It is at a minimum. It's square at 0. Okay? If we square the values, though, we can then look at the absolute value. Okay? But we also take into consideration that the further deviations you get from this line of best fit, the more it should count. So square values, remember that square really does put a huge emphasis on proximity. So the closer values, when you square them, aren't going to add up to a whole lot. But as soon as you start deviating by 2, by 3, or 4, like here, this is a deviation of almost 3 or 2.5, that's going to have a pretty substantial squared difference. And if you just want to take a look at, here's the residuals of LM1, and I'm going to square them, and you'll see, look at what happens. You have 4, 1.69, 6.76, 1.21, and 0.64. So by squaring them, you make a big difference when these deviations, when these residuals get larger. And as soon as they get larger than 1, then they start adding up. And those deviations, those residuals, or there's errors in your estimation and your prediction, start adding up to large values. Now the least squares, remember going back, I'm going to scroll all the way back here, Legendre and Gauss contributed to regression by this idea of least squares. So least squares are the idea that the squared deviations, when you sum them, will be the absolute least or the lowest number possible for the line of best fit. And if I took the sum of the squared deviations, the sum is 14.3. Now, that 14.3, I can find it from a regression, but the easiest place to find it is by looking at the summary of an ANOVA table. And if you look at the residuals, because that's what we're looking at here, the sum of the squared residuals is 14.3. So that's what we're going to be doing in this class, is I'm going to be walking you through hand calculations of each one of these things and then tying it back to output so that you can see exactly where all of these numbers come from. And as you see here, they come from a very straightforward piece of summing the squared deviations or the squared residuals, and that squared residual is the minimum, and that's what the least squares criterion is. It is the least sum squared residual that you can get from any line of best fit. Therefore, this line that was drawn and arrived at through this calculation, this line is the line of best fit. So this is the second video. The third video, I'm going to walk you through the calculation of B and A so that you can see that the least squares calculation is a lot less cumbersome than all of what we're doing here, but you'll see that it's straightforward. Okay, stay tuned for the next video in the series.